Hi everyone, I'm Susanna and this is the paper In-Context Learning as Maintaining Coherency, a study of on-the-fly machine translation using large language models. This is work done together with Kevin Du. So in-context learning, how does it work? Well, in-context learning is the phenomena where given instructions and a set of examples, large language models are able to perform the task which they were not explicitly trained on and without any gradient updates. Now, the following example presents the task of translating from English to Chinese. After the last sentence, the find also grants insight into the evolution of feathers in birds. The model should then output the Chinese translation. So why should we care? Well, this is a big breakthrough in general NLP model capabilities, but for MT specifically, why do we care about in-context learning as compared to, say, just using supervised MT? So first, in-context learning presents a paradigm shift in deploying models for NLP tasks. One model can be deployed for multiple tasks, and we want MT to be better and better in such settings. Second, in-context learning could be a way which we can adapt to different translation inputs on the fly, be it translating between different languages or just when the model encounters domain shifts in the input. Now, for machine translation, the ability to adapt on the fly is particularly interesting because it reduces the reliance on engineers explicitly fine-tuning for each domain, or even having to know the domain beforehand. Now, in this paper, we asked the question, how to prompt the large language model for machine translation, especially when adapting to different domains, or in the setting when there is a longer conversation history. So not just translating between a single isolated sentence, but as part of a document, paragraph, or even like a full conversation. Which, if you think about it, practically speaking, is a much more likely scenario than trying to translate a single isolated sentence. From an academic perspective, it is not yet clear what is the best way to prompt an LLM for machine translation. I would even say that's quite understudied, since in-context learning is popularly thought of as learning from examples. Several previous work therefore designs prompts based on similar examples to the test query or test source sentence. So typically, similarity can be quantified either with word overlap, BM25, sentence embedding similarity, or whatever you might think of when you're trying to do information retrieval. Well, in this paper, we challenged that assumption of similarity-based prompts. So, and we propose something called coherence-based prompting. So consider how LLMs are trained. They minimize the cross-entropy loss on the next token given all the previously seen tokens. This suggests that when we are translating from source language X to target language Y, with U-prompt examples, we might want to have some form of continuity or coherence with our prompts. So I keep using the word coherence, but what is the definition for this? From the linguistics literature, coherence reflects the overall semantic and syntactic consistency in a body of text. So we're not giving explicit measure for it here right now, but we are just giving the idea of what coherence is. And we can study this at both the domain level and at the document level, where domain refers to a style of writing or subject matter, and the document coherence just refers to keeping the same thread in a document. So domain coherence refers to the we test this by doing the prompt bank of the in domain versus the out of domain. And for document coherence, we test this by sampling from moving translation window within the document. I'll now explain the domain level experiments. We use three models, GPT-Neo 2.7 billion, XGRM 2.9 billion, and Bloom 3 billion, which are open access LLMs available on Hugging Face, and they are all developed by different companies and trained on slightly different data. The later two have been trained as multilingual language models, and the GPT-Neo is trained mostly as a monolingual English dominant language model. So we also experimented with OPT, but find that its in-context MT abilities were nearly twice as poor. We work with 4 datasets, WMP19 biomedical, MTNT, which is a social media dataset, TED Talks, Flores, which is a Wikipedia-based dataset. We focus on English to French translation direction, which is common across all datasets, and where all the models have some reasonably good performance. So except for medical, all other datasets have a range of topics in the trained prompt bank and test set, which are shuffled during random sampling. We use standard train test splits with the train set being used as the prompt bank. So the question here is, do models adapt within domain prompts? If models are adapting to the domain shown in the context, then sampling and testing within the same domain should result in the highest translation performance compared to being shown examples out of domain. For example, if we are testing on the medical domain, is it important that the prompt also be drawn from medical domain, or is it sufficient to have just any language sentence pairs from any domain illustrating the translation task? Now, each row in this table indicates the domain of the prompt bank, and the columns indicate the test domain. Scores are reported using Blue, and to account for prompt selection and ordering effects, we are averaging across 5 randomly sampled prompt sets. The best results are highlighted in bold. Take a moment to look at them. So first, looking at GPT-Neo, sampling from Flores results in the best translation performance across all test sentences, even with domain mismatch. Now, this could be due to monolingual GPT being trained on a large amount of Wikipedia text. However, and we also note interestingly in the results that the second best column-wise for GPT-Neo tends to occur when there's a matching prompt and test domain. For the multilingual GPT models, Bloom and XGLM, they appear to be doing domain adaptation as sampling and testing within the same domain mostly results in the highest performance column-wise. So you see this diagonal going down when the sampling prompt bank and the test domain are the same. So GPT-Neo had some results which suggest that Flores, it's mainly performant of Flores. However, if we are trying to study what actually matters for in-context MT, we do need to control for the confounding factor of length. And this confounding factor appears in both the domain experiments and also similarity-based retrieval experiments, which are done later on. So to see the relationship between domain and length, we can plot the histogram of sentence lengths by each domain. Flores in orange has the longest sentence, while TED and MTNT have the shortest sentence. So you can see the histogram distribution. On the x-axis is the sentence length, and y-axis is the counts. Now we repeat the same experiment, but this time sampling from the shorter sentence length and the longer sentence lengths. So when choosing only 5 to 10 word long sentences, which is what I've boxed up right now, we see that performance decreases mostly, or well, decreases everywhere. There's no sample from Flores because it has no 5 to 10 sentence long bin. And when we sample from 15 to 20 word sentences, we see that the performance is decreasing for Flores. That's because 15 to 20 words is actually considered a short sentence for Flores, and the performance increases for MT, NT, and TED because that's in the much longer range of sentences. For MET, the scores are similar because 15 to 20 words is very close to the mean of the distribution, of the length distribution. So in summary, length really matters. Next, we study 2 different types of coherence, sampling from the moving previous scope translation window from within the document. And for this set of experiments, we are using 3 models, GPT-Neo, XGLM, and Bloom. The data used are TED Talks in the English to French, Portuguese, and German direction. For more information on how the data is prepared, please refer to the paper. So does document coherence of prompts result in better translations? We compare this against random and several strong baselines. BM25S, which is a submodular algorithm that maximizes the overall word overlap of all the prompts within with the test sentence and not just maximizing or retrieving individual prompts. And we also use nearest neighbor embedding from sentence embedding with a state-of-art sentence transformer. So on the furthest left column, we can see the various baselines for sampling prompts, either within or outside the document, and applying random neural network embedding similarity BM25 or BM25S, which stands for submodular. We see that the last row, from sampling from a moving window within the document, outperforms the best baseline on nearly every setting. And this is quite a strong, consistent result across models and language directions. And to try and sanity check what's happening, we also quantify the similarity with L2 distance of the source sentences and the prompt sets, and also the test and also the coverage score, which is equivalent to a root 1 precision score, which is just like a word overlap score. Now, if translation performance is due to word overlap or similarity, then we expect that having a higher coverage or lower L2 would have better performance. But note that we see that this is not the case. The best performing row neither has the lowest L2 or the highest coverage. Note that all similarity-based retrieval methods depends only on the source sentence and is model and target language independent. The single coverage and L2 value applies for all results columns. Okay, the main takeaway here is that the moving window outperforms similarity-based baselines. The gains are from half to 2.6 blue points from the next best performing retrieval methods. And our sanity check shows that the performance is not due to similarity or word overlap. One natural question that you might have is, what about similarity-based retrieval within the document? So how well do similarity-based retrieval methods perform for the previous on-the-fly translations? We established that using a moving window outperforms retrieval from outside the document, and now we're going to look at what happens when you use retrieval methods from within the document. So here we only retrieve translation examples that are done prior to the test sentence. So this reflects a live translation or streaming scenario. Now, in doing retrieval-based methods within the document for an on-the-fly setting, the length does factor in, and longer sentences are retrieved on average. Because if you have high sentence that's long and has many words, then you are more likely to have higher word overlap. So we actually do some sampling with budget constraints, which is that we investigate budgeting for the length constraint to be the same as the moving window. And for every test sentence, we compute the budget used by its moving window and apply a length constraint for the other retrieval-based methods. So without any budget restriction, performance of the retrieval methods outperforms the window. However, when restricted to the same budget, we find that the performance is within 0.1 to 0.5 blue score difference. So orange being when restricted to the window budget, and blue when there is no budget. So we do some further analysis on other ordering effects within the window, or within the document actually. And we compare window with other baselines, which may give some indication of what's actually important in the document in terms of local coherence. So the static retrieval method refers to the first window translation sentences of the document, which is then held fixed throughout when translating for the rest of the document. Shuffle simulates whether the model is affected by the order of the sentences. So it's the same set of sentences as the window method, but with them shuffled. So interestingly, shuffling the set of prompts within a moving window, which does break the natural ordering of the document, does not deteriorate in-context translation performance. We do see that this is uh, we do see that there is an effect on perplexity, as you would expect, because there is higher perplexity when the sentences are not correctly ordered, but this does not actually affect its performance. And this finding is consistent across several models and languages. The ordering of the document does affect, as I mentioned, the perplexity, increasing from 11.1 to 12. And this suggests that the relationship between perplexity and translation is not totally linear or not totally direct. And overall, this suggests we may benefit from methods which perform selection from within the document, which we leave to future work. Alright, in conclusion, in-context learning has typically been thought of as learning from examples. And in this work, we try to introduce a different perspective of coherency of the context with the test sentence. And we studied this using both domain and document level experiments. For domain, 2 out of your 3 models are able to adapt to different writing styles. And at the document level, a moving window is up to 2.5 blue points better than similarity-based retrieval methods from outside the document. So what are some future work? There could be other features that are more predictive of downstream performance or better for in-context MP, such as activation of attention patterns from source to target during generation. So we mostly looked at pretty superficial methods, I would say. And another future work or limitation is that in the window method, most of these, everything that we use in the window method is based on Go translations, because we're mostly studying what the effect of this is. But in reality, you are unlikely to have a moving window of Go translations. So some work such as generating examples on the fly from the document could be useful to look into. Okay, that's all I have. Thank you very much for listening.